All right, so today we're going to move on to the other type of charging, which is induction. And as you can anticipate, induction then is charging without direct contact between the two objects. Now, remember back last time I did the demonstration with the plastic rod and the little slips of paper, right? I took the plastic rod and I rubbed it with the fake wig material, which was charging by conduction. But then those little things of paper, did they have a charge at the beginning? No. So why on earth did they fly up to the charged plastic strip? Okay. But if the papers didn't have a charge, would they be attracted to a positive or a negative charge? No, because if one of the charges is neutral, then there's not an electric force. So something else had to be going on to cause those little strips of paper to jump up to the plastic strip when before they didn't have a charge. And what actually happened to them was they were charged through induction. Just by being near the charged strip, they became charged themselves. So let's talk about how that works. We'll start off with a positive sphere again. And this time, instead of allowing it to touch the neutral sphere, I'm just going to bring it really close. If I bring it really close, but don't let it actually touch, what's going to happen in the neutral sphere? Okay, they'd love to jump over, but let's pretend like this gap is too big to where they can't jump. Where are they going to go? If they can't jump, they're not going to the side, right? They're going to start crowding over here, aren't they? Because they are attracted to the positive charges even though they can't get to them. Now, if these electrons line up on the left side of this sphere, what does that mean about the right side of the sphere? Yeah, they're leaving behind lonely protons, right? So they're leaving holes, positive charges. Now, this sphere, is it neutral or does it have a net charge? It's neutral, right? I still have even numbers of positive and negative charges. So there's still no net charge. But something's going on. What do I have? What do we call this when you're positive at one end and negative at the other? Polar. It's polarized. And we call that polarization to be a temporary, and you'll see why in a second, induced partial charge. Now, yeah, lots of adjectives. This adjective, right, induced because there wasn't actual touching, right? There wasn't contact. It was by induction. Partial because, yeah, there's no net charge. This side is partially negative, and this side is partially positive. And by the way, that's the lowercase delta in Greek. If you don't want to draw the fancy delta, you can just use a little d. Little d and little delta in math and science mean tiny things, right? So this is a partial charge. It's not really negative, it's just partially negative. And that's this polarization, right? Now, let's take a time out there for a second and talk about that. Where have you learned about a polarization like this? Water molecule in chemistry, right? What's the shape of a water molecule? Okay, it does have two hydrogens and an oxygen. I'll give you multiple traits. Multiple choice. A, B, C, or D? C, right? It's bent. The reason it's bent is because there's two pairs of unshared electrons and two pairs that are shared with the hydrogen atoms. So therefore, those unshared pairs push away harder than the shared pairs. And it gives it this bent shape. Well, but look at that bent shape. What do you see? This end right here has a lot of electrons, a lot of negative. So it's partially negative, meaning that this end is partially positive. The polarized nature of water molecules lends itself to what phenomena that you learned about in chemistry? Okay, yeah, little beads of water because the surface tension, the cohesion of the water molecules. They grab onto each other because of the hydrogen bonds between the molecules. What else? How about adhesion, where water molecules stick to other things? You heard of capillary action in plants? It allows the water to climb up tiny tubes because the water reaches up and grabs the sides of the tubes. And then it pulls itself up by cohesion. So we have adhesion and cohesion working together to cause capillary action. Yeah, when they take your blood, they use a little tiny capillary tube to then suck it right out. They don't have to apply a pressure. Good. Anything else due to the polarized nature of the water molecule? Yes, there is. It's also part of the reason that you get the crystalline structure of water that makes ice less dense than liquid water, which is important. Right? Otherwise, when ponds froze, they would freeze from the bottom up and kill everything. Instead, they freeze on the surface, preserving the life inside. It's also how what appliance in your home works. Microwave oven. We'll talk about electromagnetism later, but you'll see how the polarized nature of the water allows the microwave to work. Because it's actually heating up the water molecules in the food. That's why the food gets hot faster than the plate. It's also why pasta heats up relatively easily in the microwave, whereas bread not so much. All right, so that's why it's called a partial charge. What about temporary? Why do we say it's temporary? Because if I move this guy over here, then what's going to happen to those electrons? Exactly. These guys aren't attracting, or these girls aren't attracting these guys that much anymore. And so these guys turn around and say, oh, well, yeah, I guess I'll head back over to these ladies over here, right? And there we go. And so it ends up going back to being not only a net neutral charge, but also no partial charges either. So that's why I call it temporary. All right, so far so good? Now, what if I did this, though? Let me get this out of the way. What if I connect what's called a ground wire? And a ground wire goes where? In the ground. In the ground. But it doesn't have to be in the ground itself. It can be to any large area where the charges can spread out. So for example, whenever I get out of my car in the winter, especially if it's really dry out, I don't want to shock myself, right? So as I get out of the car, electrons are being scraped onto my clothes by what? conduction, right? There's contact, and so they're scraping them off, kind of like I did with the plastic strip. So I'm scraping electrons onto my body. If I just get up like that, those electrons are on my body. When I reach out to touch something, they'll jump off, right? Because they're built up and they're wanting to get off and they have no way to get out. Instead, if I reach around and touch the car door as I climb out, as I scrape those electrons off the seat, they go straight to my hand because they'd rather spread out more. And the surface of the car acts as the ground. It allows them to spread out over a much larger area. And so as I get out, they run through my hand, and so none of them stay on me, and I get out, I'll shock myself. And we'll show a video clip a little bit later about that. So a ground can literally be to the ground, which we'll talk about when we do electric circuitry, or it can just be some place where the charges can spread out and get away from each other. Either way, if I have a ground line connected when I bring this positive charge up close, what's going to happen? What's going to go to the ground? Positive charge is going to move to the ground? Or negative charges are going to go from where to where? From the ground to those positive charges, right? Because those electrons, remember electrons are free to move, and so those electrons down in the ground look up and they say, hey, see those ladies that got left by their men up there, right? And so they kind of mosey on up there and start small talk, right? And cancel out those positive charges. As a result, now what does that sphere have? It has a net negative charge because it has more electrons on it than it has protons. Now, what happens if we move that positive sphere away? Who? Well, it could be, except picture yourself as one of these electrons right here. Yeah, you're looking around, you're saying, there's way too many dudes at this party, right? And so you say, well, down here, there's still about a 1-to-1 ratio, right? There's lots of ladies still down on the ground. And so what do? That's right. You head back to the ground. As a result, what happens to this negative charge? It goes away, and so we're now left with a neutral sphere again.
Wait, are there still 4 positive and 4 negative in there, though?
Yes, they're just neutralized. Good. Yeah, there's still charges, but there's equal numbers of positive and negative. Yes?
Where do the negatives on the left side stay down? Or where do they go?
Yes, the extra negatives went down to the ground. So now there's even numbers again. Make sense?
Wait, okay. So for the first time that you did it, when it connected to the ground wire, the negative one came up to the top, but that would leave you with tons of electric ones. So the other electric ones over there, how do you say that? The other negative ones up there went down?
When I move this away, right? So long as this guy's close, then those electrons crowd over here, making room for more electrons to come up from the ground. But as soon as I move this away, now there's nobody pulling anybody over here. They go back to normal, and that, in effect, pushes those negatives back down to the ground. All right? There's a ground wire here, and here. And if you look under your hood, you'll see all kinds of wires running with little green screws. Those are ground wires because they're going from somewhere where there's a source of charges to a nice spread out area so that the charges don't collect in one place and shock you. There's one, and again we'll get to this when we talk about the electricity in your house, but if you go out by your electric meter and look down on the ground, you'll see this, the top of this metal pole. That pole is like 6 or 8 feet long, driven down into the ground. That's where the ground from your house goes to the earth. So yeah, so there's lots of them. But my hand can act as a ground too, right? If I provide, again, when I get out, if I touch, then I'm the ground wire connecting whatever charges I have to an open state. Yeah.
So say, like you were holding on to that,
Okay?
and it was plugged in, and you pulled it out, like you pulled that object and it pulled it out, why can that shock you?
Because as we're going to see in a minute how this works, the charges will have already come from this ground and collected on the sphere. But then once they shock me, if there's not a continual supply of the charges, then it won't shock me again, right? If you rub your feet on the floor, right, and go over and shock your brother, then can you shock him again? No, because the charge buildup has already discharged and jumped onto him. And so unless you build up more,
So why does it shock you?
why
Like,
does...
because if you touch it and it's not shocking you, but then you pull it out and it unplugs, why does that shock you?
Well, it only shocked me once. And
Well, I'm saying because I was like holding on to something and I pulled it forward and it unplugged it. And I didn't know and it shocked me like it really badly. And I didn't know why.
I don't know. I mean, unless there's like a short in the cord, maybe. I mean, if that's happened over and over again, to where the wires maybe were loose. I don't know. That's weird. Which is why you shouldn't pull things out by the cord, right? Okay. She didn't mean to. All right. So now let's do this again and see what's different this time. I bring the positive charge really close to the neutral. What happens? Yeah. Get your John Williams songs right. Come on. All right, anyways, the electrons crowd over to this side, which allows the electrons in the ground to want to crowd up and neutralize those positive charges, giving it a net negative charge, right? What if I do this? What if I cut the wire and then move it away? That's exactly right. How'd you get? No, what is it? What happens? Well, if it's allowed to move, yes, it'll follow it. But what's true about this sphere now? It has a negative charge. It has a permanent induced negative charge. Why? Why is it permanent?
Would you please send Wesley Gian to the front desk for just a moment?
Sure will. Hey. So, why? Why is it permanent now?
Because there's nowhere to go.
Exactly. I cut the ground wire, right? The charges have nowhere to go. They can't run away anymore. Do they want to?
Yes.
Absolutely.
Wait, this happens when the wire is cut? Yeah.
If I cut the wire before I move the positive sphere away. Right?
I have a question.
Yes, sir.
The positives are still gone from there, correct? The positive charges?
What do you mean by
That
positives
were-
are gone?
That were on the right side.
They've been neutralized by negative ones.
Okay, so overall that is charge negative.
Yes. There is a net negative charge now. Yes. As a matter of fact, yes, if both of these are free to move, then they're both experiencing what? Yeah, an attractive force. And so if I let them go, they'll touch each other, and then what will happen? By conduction, these negative charges will cancel out those positive charges, and I'll be left with two neutral spheres.
And what did F stand for again?
Force, electric force. All right?
Wait, so if you cut it before you move the positive A,
If you cut the wire before you move the positive away, then those negatives are on the sphere, right? And if I cut the wire, I don't give them a way of escape. And so they have to stay on the sphere. All right? Okay.